This is the screencast for section 3.3, example 6. The power rule does work for negative integer powers or negative exponents, as you may or may not have guessed. So let's get right to it. We are going to find an equation for the line tangent to the curve. So now your first instinct may be, well, wait a second, I have to find an equation for the line tangent. I need to find the slope of the tangent, so I need to take the derivative, which means I should use the quotient rule. But wait, why use the quotient rule if you can avoid it? The quotient rule is pretty messy. I'm going to rewrite y as x squared over 2x plus 3 over 2x, which is also the same as saying, 1/2 x plus 3/2 x to the negative 1. And now that I know for sure I can use the power rule on negative exponents, I can tell you that y prime is, okay, the derivative of 1/2 x. Let's see, that's x to the first, so drop the 1 as a coefficient. That's going to be 1/2 times 1, which is 1/2, and now x is going to be to the 1 minus 1, or 0 power, so I don't need to worry about an x, plus, oh, wait a second, my negative 1 is going to drop down as a coefficient, so that will turn into a negative 1, and then times 3/2, but now x will be to the negative 2 power. So the derivative, to help me find the slope of the tangent at the point 1, 2 that the instructions are asking for, will be 1/2 minus 3/2 x to the negative 2. So let's find y prime of 1. So the slope of the tangent at x equals 1 is 1/2 minus 3/2 times 1 to the negative 2. So that's 1/2 minus 3/2, or negative 1. So my slope is negative 1, and I know the point. It's 1, 2. So the equation of my tangent line is y minus 2 equals negative 1 times x minus 1. And we want to support that graphically. So what I did was I graphed the original equation in y1, and then I graphed what my tangent was in y2. I just added 2 to both sides to be able to graph it. So I put in y1, negative 1, and then x minus 1 plus 2. Graphed it and made sure that they intersected at the point 1, 2, because the line is supposed to be tangent to the curve at 1, 2. And it is. So now try problem number 27. Says find an equation for the line tangent to the curve at the given point. This problem looks very similar. The last one, the only change was it was x cubed plus 3. Well, fine. But now I can still, oh no, now it's x cubed plus 3 in the numerator. So it is a little bit different, but I can still avoid using the quotient rule. I know we have a quotient, but if we can avoid using the messy quotient rule, we will. So I'm going to rewrite y first as x cubed over 2x, and then plus 1 over 2x. So that would be the same as saying 1/2 x squared plus 1/2 x to the negative 1. And now I get to use the power rule to find the derivative. So y prime equals 2 times 1/2, which is 1. X to the 2 minus 1 is 1. So I don't even need to write that. Now we have negative 1 times 1/2, so it's going to be minus 1/2. And then x is now going to have a power of negative 2 because I subtracted 1 from negative 1. I'm looking for the slope of the tangent at x equals 1. So y prime of 1 is 1/2. So the slope of the tangent is 1/2. Well, I need to make the equation to the tangent line, and I only know the x-coordinate of the point, so I need to plug 1 back into the original function. So y itself of 1 is going to be 1 cubed plus 1 over 2 times 1, which is 2 over 2. Also 1, how boring. So now the point is officially 1, 1, and the slope is 1/2. So the equation of my tangent line is y minus 1 equals 1/2 times x minus 1, and I'm going to verify that graphically by graphing the original function and my tangent line. And I made sure that they intersected at 1, 1 by finding this intersection here. Now they do intersect over here, but this line isn't tangent. It doesn't run along the curve like this one does. This one just cuts through the curve. So this is where the curve and the line I created are tangent to each other.